Hi all, welcome to the week 8 tutorial. We're going to be talking about kernel methods and support vector machines of various kinds. So let's start. When we think about, let's talk about this in the context of a linear classifier first and foremost. Hopefully we are somewhat familiar with this setup where we have two classes, a positive class and a negative class, and we want to find some way to separate the two and create some sort of classifier so that if there's some sort of new instance, we can create our prediction or best view as to whether it's positive or indeed negative. Now, this line here, I mean, we can clearly see just judgmentally that it appears to work quite well, but there's actually many different ways we can go about doing this. There's actually an infinite number of ways we can go about. There's an infinite number of ways we can go about drawing this sort of separating line or hyperplane. If we draw this out to if we generalize this out to more dimensions. So then this raises the question: what is the best line? What is the best separating line or hyperplane if it's in more dimensions? There's quite a few different ways we've gone about doing this so far, and you can think about in terms of us building a linear classifier. We've seen things like centroids. So here, if you build a centroid-based classifier, right, you have a centroid say here, and a centroid say here, and there'll be some sort of there'll be I guess a decision boundary, if you will, where if you're on this side you'd be blue or positive, and if you're on this side you'd be orange or some sort of red, and you could have done some sort of naive Bayes or logistic regression. There's a variety of different ways. There's also the one closest to what we're going to talk about today with the support vector machines might be the perceptron learning algorithm. It directly forms a separating hyperplane. So unlike some of the other algorithms here, where you don't directly form necessarily a separating hyperplane, it may be more implicit. There's a decision boundary. The perceptron learning algorithm, you may recall, you'd have your straight line, or even the basic linear classifier, the equivalent, the basic linear classifier, or just your perceptron, and you iteratively go through the data set and nudge the weights up and down until there's no further misclassifications. Okay, so let's talk about this a little more. What's the word? A little more. I mean, let's have a think about it. If we, as a human, were to draw a line, let's have a think about the ways we go about, deciding what is the best, separating hyperplane, right? One way to go about doing this would be to, you want to find a line, right, in the middle between your two classes where, the distance, right, from each class to the separating line is maximal, right? So the distance, maybe I'll draw it out here. Now what? Selected portion. Right. So judgmentally, you might think of one way to go about finding this line is to find the one which in some way maximizes the distance between this separating hyperplane and the data points on either side, and that's exactly how our support vector machine. That's exactly the framework of the support vector machine. So we are trying to find the maximum margin, right? This distance here is called the margin, right? The distance between, the data point that is closest to the separating hyperplane. So this is the separating. This is a separating hyperplane here, right? And this is the distance between the separating hyperplane and the closest point you know, of each class to that margin, right? This is the entire concept between the support vector machine. We want to maximize, you know, this margin, right? So back up above here, right? So, you know, I think hopefully that makes some intuitive sense. We want to find the line, you know, where the distance between each of these clouds, if you will, is the greatest, right? We don't want necessarily this one. And the thing about all these lines is all of these red lines, they classify both of these, they classify this data set perfectly, but it's a point of finding, you know, what is the best one. And, you know, under the support vector machine criteria, this red line at the bottom here, it wouldn't be the best because, you know, the margin would be quite small, right? We might want something more like, say, perhaps this line here, you know, where it's got a decent margin here and then, you know, decent margin here, here and there as well. Okay. Maximum margin separating hyperplanes. So this is what we're going to talk about here today, and this is the concept that underpins your support vector machines. One thing to note, though, however, is that it may not always be possible to generate a separating hyperplane. So take for example this classic, the classic exclusive OR problem. So you know, you can think of a truth table. We have two inputs, x1, x2, and you know, one will be mapped. Well, let's say true is mapped to 1 and false is mapped to 0. Now there is no way to draw a straight line that can separate, you know, the positive, which is this point here, and this point here, with the negative, right? With and it's fine. You know, any line, you know, you can shift this line this way or that way. Any line that just, you know, separates any line that sits above 0, 1 and 1, 0, and you know, below 1 and 1 will do. This one's quite straightforward. This one you can't. This one you can think of many ways you can draw a separating hyperplane. This one is a little trickier. So we say this is not linearly separable, which just means that, you know, you can't draw a straight line to separate the data set. Right. So there are some extensions. There are some extensions on, I suppose, your support vector machine. Other ways to make it a bit more powerful. Which order they talk about it here? Yeah, maximizing the margin. Yeah, there's a few ways to make. So you might think to yourself, right? This basic support vector machine, it does seem quite limited in the sense that, you know, in these examples so far they are perfectly linearly separable. But of course, we all know in real life, right? You know, things aren't great. Things that data is often not perfect. You know, it could be there's a minus here, maybe there's a plus here. In which case, this form of the support vector machine, you know, it wouldn't really do. So there's a few different, I suppose, types of support vector machines. Let me just pull this out here. Right, this is the one that we learn about first, so it must separate it perfectly, right? There's no room for error. The way this is set up is there's no room for error, and of course this is you know, unlikely to be very useful in real life, given that data is often noisy and it's, you know, often not possible to find a perfect classifier. You have also the next advancement, I suppose, the next on your support vector machine would be your support vector machine with the soft margin. Now, what do I mean by soft margin? So soft margin basically means there's a slack variable. There's a bit of a budget for error. Things don't have to be perfectly linearly separable. So let me pull it up. Okay. It appears later on, but it's in the context of the Lagrangian, so maybe I'll speak about it then. But the thing to keep in mind is you have several forms. Your most basic one, everything has to be perfect in a ways. Then you have your soft margin SVM, and then there's a tolerance for misclassification. So it doesn't have to be I guess, perfectly linearly separable, right? But even so, this is still linear, right? So you're still using with a soft margin, this could be a soft margin support vector classifier. So you have things on both sides which make it stop it from being perfectly linearly separable. But there's a bit of a tolerance. There's a bit of a tolerance for error. Say here and here, right? But still, you're using a straight line. You're still using a straight line to try and separate things. Which may not always be the best thing in the world. So the next extension is we have what's called a kernel function, and there's quite a bit to unpack in terms of the kernel function, right? So the way you can think about the kernel function is you map you map the data into a higher dimensional space, such that and in that higher dimensional space possibly there's a way to linearly separate the data. I think this is easier to explain with a diagram, right? So take this data set on the left here. You have your x's, you have your noughts and crosses, you have your x's and your o's. There's no way to draw a straight line or hyperplane that can perfectly separate it, right? But if we were to project this into a three-dimensional space, some sort of R3 kind of space, right? We've gained an extra dimension. Now there's a Z3, right? Of course this is 2D, so it might not be easy to see, but there's a plane here that can perfectly separate the noughts and the crosses, right? So this is the concept behind the I guess the support vector machine with the kernel trick. So I'll explain why it's called a kernel trick in a moment, but the thing I want you to keep in mind is that it allows you to deal with non-linearly separable data because you're projecting it onto you're mapping it to a high dimensional feature space, right? And then possibly you want to try to find a dividing hyperplane there. Now of course this begs the question, how do you know this? In practice there's a lot of different kernel functions, there's a lot of different I guess mappings, right? And you sort of test them all and see which one looks best, perhaps under some sort of cross-validation or training validation test split. Okay. So that's a bit of a primer. As to the different types. So where are we up to? Up to here, extending. So this is the extension of the linear classification. This is what they're talking about here. So you're mapping it into a new feature space and looking for some way to find a separating hyperplanar line over there. Now, the next concept I want to talk about is the dual form. So a dual form, effectively what it means is it's an alternative way of solving the same problem. So you rephrase some problem, say here optimization problem, into another form that's maybe easier to deal with, and solving the equivalent problem in another form will solve you the original problem, right? And we use this dual form in our I guess our optimization problem here because it just makes the math a little nicer. Okay, so the easiest one to understand first off the cuff, before diving into support vector machines, we can look to understand the linear classifier, I guess the basic perceptron learning algorithm in dual form. That is easier to digest than jumping straight into the support vector machine. So at this point I might segue out to here because this is effectively question one. Question one of the tutorial just wants you to understand the perceptron training algorithm, but also B, how it is in dual form, right? How it is in dual form. Okay, so just a bit of revision. your perceptron training algorithm, right? It's basically a linear classifier. You're trying to draw, a straight line. So the setup, you might have, like green and red, and you want to create some sort of, line that can separate the two. Something like this, maybe. Something like this, maybe. And you want to use, this is a basic perceptron, and you want to use this algorithm to try and learn whatever weights this this may be. I mean, keep in mind, you could express this here line, I guess something like this, right? It's equation of a straight line, and the t might be on this side or this side. You can make it negative and equal 0, whatever. But this is just the basic equation of a line slash hyperplane, right? Question is how to get these weights, right? So effectively what you do is you would cycle through the data set, right? And this is when there's a misclassification. This is a misclassification, and when you go through when there is a misclassification, you would bump up and you nudge the weights, right? You change the weights. So you cycle through your entire data set, and every time there's a misclassification, you'll change the weights, right? And you keep doing this until there's no more weight changes. Stop when no more weight changes. And then we say we've converged. Okay. So, what is the dual form? The dual form, it's an equivalent. It's another way. It's an equivalent, another way to express the perceptron learning algorithm. So let's pick this apart and hopefully understand why it is equivalent. So what's similar? We are also cycling through the entire data set. So 1 to D. So loop through all data, right? And given this, if it's negative, then let's do something, right? But what is this? This is our prediction, isn't it? So you can see here, the weight vector you can think of as the cumulative bumps and nudges. The cumulative bumps and nudges every time there's a misclassification. So the weight vector is just the cumulative bumps and nudges from all the misclassifications in the data, just based off this. You will remember the weight only changed when there was a misclassification, and we initialized it as 0 anyways. So this alpha here, you can think of it as an indicator as to, whether to bump or nudge. Or maybe you can think of it as, oops, sorry, it's a bit loud. Think of it as, number of nudges. Number of from that, piece of data, right? So starting at the beginning, this would all be 0. I want you to think of this as effectively y hat, and of course this is also y hat. It's the the predicted value, but this predicted value has just been expressed in this sort of dual form. So what is this predicted value? It's these are the weights, right? These are the weights. Okay, your weights multiplied by your x. Okay, and so what happens is you go through the data set, and this alpha keeps track of the number of nudges that you need. Okay, so hopefully you can sort of see how these are equivalent, right? So here you explicitly set the weights here. Here you instead of explicitly setting the W, you keep track of the number of bumps and nudges from each bit of data. So this is basically the weight. You look at the number of nudges, which is alpha, from each for each piece of data. J is equal to 1 all the way to the cardinality of D, or the number of observations. So hopefully we can understand that the weight vector can be seen as the cumulative nudges for each misclassified instance. So this is the, I guess, the number. Number of nudges from some sort of misclassification. Right. So hopefully that gives us a bit of a flavor as to the perceptron training algorithm in your dual form. Okay. So this will hopefully give us a bit more of an understanding when we try to apply this dual form concept to the support vector machine. Okay. Kernel Trick, right? Yeah. So let's touch on the Kernel Trick briefly, and then we can it might be a bit early to talk about it, but the Kernel Trick is basically a way of finding. It's a function which tells you the dot product of a mapping. So what I'm trying to say is, let's say you have a mapping from, say, this space to this three-dimensional space, right? If you have some function which tells you the dot product after you've mapped it from R2 to R3, that's your kernel function. Okay, so let me repeat that. So you have some mapping from R2 to R3. If you have a function which tells you the dot product of, you map it to R3 and you get the dot product, then you can basically skip mapping it to R3 and then calculate the dot product. The function will tell you directly, right? And why it's called a kernel trick is, in the concept of support vector machine, we really only care about the dot products between the features, right? So the kernel trick allows us to map things to a higher dimensional feature space, and then get the dot product and calculate the support vector machine without actually having to map it to a high dimensional feature space. So we'll see this a little bit in a moment. But remember, a kernel function in general, right, tells you the dot product of after mapping something to another space. Okay, so let's talk a bit about how we actually train about this, how we go about training the support vector machine. There's a few things to keep in mind. So why is it called a support vector? Interesting thing about support vector machines is that they are 100% defined, purely defined by the support vectors. Now the support vectors are the closest examples of each class to the separating hyperplane. So on this side, so I guess the white, or maybe the negative class, we have two support vectors, because these two are the exact same distance from the separating line, and they're the closest. On the black side, on the positive side, this is the support vector because it's the closest, and then there's no one else that is as close. Now, with the support vector machines, you can change everything. If you change a point, if you delete a point, if you get rid of a point that's not a support vector, it won't change anything. If you add a point out here, that isn't closer to this hyperplane, then it won't change anything, right? So another way to think about it is the support vector machine, in a ways, or the separating hyperplane, rather, is defined by the support vectors, the vectors, or the points closest to the separating line. Right. Yeah. So we got a bit of mass here. So you can express the separating hyperplane like this. This is a general form of some sort of line or hyperplane, right? Now, there's a bit of geometry, going here, but you can express this W vector. So this W dot X is equal to T is the line, right? Is the separating hyperplane, and the gradient is W, right? And you can think of it as this problem as minimizing this W, right? subject to some constraints, right? And this is the dual form. You can use the method of Lagrangian multipliers to express this minimization problem into this expression here, which is easier for us to deal with, right? And then so once we have this expression here, then we basically want to minimize it. We want to find the optimum with respect to the alphas, right? We set them to 0 and use the constraints, and then we can. That's it. Then once we solve that, then we have, I guess, the parameters for our support vector machine and the separating hyperplane. Okay. There's a few details here, but I think it's probably a bit easier if we go to the tutorial questions. We add a bit more flavor. But yeah, one interesting thing I do want to talk about here is that so the earlier examples before, we looked at what's called the hard margin classifiers, which means that they're perfectly linearly separable. So in this example here, the hard margin classifier, it just wouldn't do. There's these blue dots here and there's a red dot here. You can't, right? So the soft margin classifier actually has this slack variable here, which just gives you a bit of a budget for error, right? And if you have more slack, there'll be less underfitting. If you have less slack, there might be more overfitting. There's that relationship there. But this soft margin classifier, allows for a bit of misclassification, and the slack penalty is actually a hyperparameter that you can tune. Let's jump into the tutorial questions. So we've talked about question 1. Let us speak about question 2. So this is a walkthrough example. This is a walkthrough example of of actually finding the weights and the separating hyperplane in the context of a support vector machine. So here's our toy data set. There's a toy data set because we only have three observations, and then this is the target, right? The first thing you want to do is set up a gram matrix. Now, the gram matrix, you don't really need it, but it makes it easier. So the gram matrix basically just it basically just tells us the dot product of everything. So for example, how do I say it? So over here, this is the dot product of x1 and x1. So how do I explain? So there's 1, 3, dot 1, 3, right? So that's x1 and x1. Say this one here was a 3, 2. So 3 and 2. So the dot product of this and this. But of course, you have to incorporate the class label. So you actually multiply these through. So this one will be 0, 1, but then you have to multiply the negative through, dot, and then 2, 1, which of course is negative 1, etc., etc. So the gram matrix just gives you the dot products of everything. Okay, you don't need it, but it can just make things easier, right? Now, this is the dual form of the optimization problem using Lagrangian multipliers, right? And it's derived in the slides. So all we need to do is plug this into here. So take the sum of negative half, sum of everything. So start with alpha 1, so that's 10, right? And then alpha 1 squared, because say let's start with I is equal to 1, j is equal to 1, right? You have y1, which is 1 times 1, fine. And then you'd have x1 dot x1, which is we've got a gram matrix, so we can just sub it in here, right? And then let's keep cycling through. Let's say, just zoom in a bit. So in this example, we'll say we have this is I is equal to 1, j is equal to 1, right? sorry, and then we'll cycle through replete. So I is equal to 1, j is equal to say 2, right? And you just basically just sub it into this this formula here, which is the Lagrangian form. Okay, and of course don't forget about the terms at the end, right? So remember, this is the dual form. This is the goal of this is to find the weights, which find your weights which have your maximum margin, right? And with our optimization problem, we typically want to take a partial derivatives, to find let's say the problem looks something like this, right? We want to find this. Oops. We want to find the minimum here, say. Well, this is the maximum, isn't it? Sorry. So let's say the optimization problem looks something like this, right? And we basically want to find the maximum, and it might look something like this. Again, assuming it's convex, right? And this would be the point where I guess, what is this, alpha 1, alpha 2, where del alpha 1 equals to 0, but also del alpha 2 equals to 0, and that could perhaps be some kind of maximum, right? This is what we're trying to do here. So we had the original optimization problem to find the maximum margin classifier. We express it in a dual form here, using Lagrangian multipliers, which gives us this formula here. We can plug it in here. The Gram matrix is just used to make things easier. It's just the dot product of everything, right? So to get from here to here, just plug it into this formula, right? And step 3, we want to take the partial derivatives because we want to find the maximum here, right? So we set everything 0, and hopefully that's the maximum, right? We do that. We take the partial derivatives, we do that, and we solve, and we end up with alpha 1 is equal to 1/4, and alpha 2 is equal to 3/8. Now don't forget about our constraint here. So where is our constraint? Here. We have a few constraints, so we can use these constraints to help us out in terms of solving for the alphas, right? Now the other thing we know is that remember the support vector machine is purely defined by its support vectors, and keep in mind these alphas are an indicator of whether it's a support vector machine. So support vector machine is a separating hyperplane defined by the support vectors. Sorry. Right. Now, this last step here says, so remember, w dot x vector is equal to t. Now, we've solved for w. I mean, w is, well, this is w, so we've got w. We can just plug in, we can actually just use any x, right? And then we can solve for t, right? Which is what we do here, and we get t is equal to 3/2, and then we just go 1 on the norm of w, and we have our margin. Cool. So this one's probably a little hairy, but try to step through each of these in your own time. The next question here is we're basically applying, so we're basically applying a support vector machine, I guess from scratch to, I guess, a real, I suppose, toy data set. So as usual, these are the features, this is the target, and in this case we're actually told what the support vectors are, right? I think we're told what the support vectors are. Oh yeah, yep. So these are actually all support vectors. right? So you can use this classification rule. We basically got to use all these guys here, right? So what we want to do is we want to use this classification rule to classify two things effectively, right? Now, what are we told? So we're told that I guess the alphas. So remember the previous question, we had an alpha associated with each data point. We're told it's all equal to 1. Just to make things a bit simpler. So what do? We have a data set here, and we cycle through all 4 support vectors, and we see what the classification is. Right. So the first, what's the easiest? Sorry guys. What's the easiest way to classify this? Possibly in Excel, or should I do it here? Draw it out. Okay. So I mean, in the first example, these are just the features here, right? Okay. And the next thing we want to do is we want to find the sum of everything, and then we add them up, and we should get to 11. So we're told alpha is equal to 1, so that's fine. And then we need y times the features, which is fine because we know what that is, right? I mean, it's just 1, right? So this is 1, that's 1, and so next thing is we need the dot product of effectively this guy here and this guy here, right? So 1 times 2, so that's 2, 0, 0, 0, 2 plus 12, 14, 14 plus 3, 17, okay? So this one here is the dot product of 1, 1, 0, 0, 3, 3, dot 2, 0, 1, 0, 4, 1, like so. Okay, and then we repeat that because remember there's 4 support vectors, and we just cycle through all the four support vectors, and then we add them all up. 17 plus 9 minus 7 minus 8 is equal to 11 here, and therefore our conclusion is that we say it's positive class. Now we do the same thing on the second guy here. So we take the dot, we take the dot product of the support vector. Say the first one 2, 0, 1, 0, 4, 1, and 1, 0, 1, 2, 3, 1, 1. Okay, multiply it by 1, multiply it by 1 again, and you repeat, rinse and repeat. You add them all up, and you get negative 19. So you say it's equal to negative 1. Cool. So that's question 3. Now question 4. So question 4, what does it ask us? Yeah, pull this guy up. I wrote that here, didn't I? So effectively, you're basically being told you have some kind of mapping right, and in this case it's from, where is the mapping? Oh, it's not so much mapping, isn't it? Yeah. You're told the kernel trick, blah blah blah. Okay, this is you take. So we're trying to explore the concept of a kernel function a bit more, and so basically this is a kernel function. Kernel function gives you the dot product of a mapping. So we're actually told the mapping is, well, it's this, isn't it? It's just this. We're told the kernel function is, and then we want to go backwards in order to find the mapping effectively, right? So we want to do it something like this, right? We're told the kernel function, so we can kind of work backwards. So we know that the kernel function is just the normal dot product between the two of them, right? So we have like x, y. We want to work out what it gets mapped to. Okay, and we're told that it's just the dot product is the same as just squaring it, right? So if we were to expand it out, it would look something like this, So just x, the dot product, and then you multiply it together, and of course, the dot product here, would be x1, x2 dot y1, y2 like this, which is of course why when you get the dot product, it would become this x1 y1 plus x2 y2, right? And you multiply the rest out accordingly. Okay. I think they just want us to. I don't know if we want to find. I don't know if we even need to find the mapping. They've changed the questions since last trimester, but we can use this to find the mapping. I think that's always quite interesting. So this is effectively what this looks like when we expand it out, and they just wanted to test it out with. To see why this is so, you take the two instances and you take the dot product x dot y and obtain the answer 7. Clearly raising this dot product to the power of 2 will give you that. Then a set of feature transformations to the original data. Okay, so it's taking a step through. This is the entire thing, isn't it? Huh. Okay, yeah, I think it does want us to find the feature transformations. Yeah. Done a set of feature. Okay, yeah. So we're given the kernel function, which is this one here, x dot y squared, and that's equivalent to some mapping, which looks like this. Have I interpreted this correctly? What is happening here? The kernel trick means it only. Let me change this question. Yeah, see what? So you take 2 and take the dot product to obtain answer 7. Fine. Okay. Okay, so what have we been told here? We've been told that which one's a kernel function? Expand this for the same answer if you had originally, plugging this into our data. Sorry, that's not it. So I looked up last trimester. This looks a little different. Support vector machines. Here. Choose. No. What was here? Support vector machines. Kernel methods. Sorry about this. Things have changed a little bit. This was that. Alright, this makes more sense. Let me grab this one. Sorry, the wording has thrown me off a little. Let me grab this and put it in the slides. this one here, put it here. There we go. Okay, so sorry about that. So our starting point, we have some kind of mapping, and our starting point is in R2, and we want to work out, where it goes to, right? And the starting point is, we have X, and Y, right? Something like that. And we are told what the kernel function is, right? And we want to work backwards to work out what the mapping is, right? So normally it's kind of the other way around, right? Normally we have some kind of mapping, and then we want to try to kind of find the kernel function. This one is, in a ways is the other way around. So what you can do is you can work backwards, right? Given the kernel function, and then work out what the mapping is. So right, we're told this is the kernel function. Kernel function, right? And it's equal to 49 here, but that's not really the most important thing in the world. I mean, they're just plugging in things. So I think the more insightful thing out of this question is to try and find out what the mapping is, right? So let's as a starting point, let's expand this out. We have x and y, two I suppose two vectors, okay, and let's expand it out. So we just have this dot this, and then it's a bit, you dot product x1 y1 plus x2 y2, right? We square it, expand it out, okay. We can see here, if we were to express it, in terms of some kind of mapping, in terms of dimensions, it would have to look something like this. So now we have this mapping, right? What is it? X1 squared, x2 squared, right? And then, well, square root 2 x1 x2, like this. So in this question, this is R3, isn't it? Let me grab this. This is our mapping, okay? And we also have the kernel function. Sorry, it should be x1, x2. We're also given the kernel function, which is just x dot y squared. So we were told this, and we wanted to find out what this is, what the mapping is, right? And the way you go about doing it is, given you're told the kernel function, right, and the kernel function effectively is, the dot product effectively is a dot product of, x and y, right? And x and y now actually comes from here. That's R3, sorry, R3. It actually comes from here, right? So you want to work out, how to express this into two vectors. When you dot it together, it turns into this. So you want to find a way where you do this, almost working backwards. So you take the dot product. If you take the dot product of this, it has to turn into that. So you have to kind of think, okay, if I go from here to here, how do I take the reverse dot product, and go from your R3 to R2? Okay. Now in terms of the whole equivalency with the 49 thing, right? Like there's what you could do is so in order to find, I guess, remember the kernel function is used to, I suppose, find the dot product after mapping. So let's test it out. Let's use the kernel function, right? And in this case, let's find it out. So what is it? So it's x dot y squared. So x dot y, that's 1 times 3 plus 2 times 2, so that's 7 squared. So that's 7. The other one is to actually map to the higher dimensional feature space and then calculate the dot product. We can do that. So what you do is you'd map it to this higher dimensional feature space, right? So and then you take the dot product. So you let's say x1, let's map x1, so we end up with what? X1 squared, that's 1, we're at x2 squared, so that's 4, and then we have root 2 times x1, x2, so 1 times 2, root 2 times 2, okay? And we want to dot it with y. I'm sorry. We'll have 3 squared, so that's 9, we'd have 2 squared, so that's 4, and then we want root 2 times x1, x2, 3 times 2 is 6. Let's take the dot, so that's 9 plus 16 plus 9 plus 16 plus 2 times 2, which is 4 times 6, so it's 24. Just like this, which is 49, which is the same as that. Which is now the same as that. Okay, so that might have been a little convoluted, but the sense of the question is you were given the kernel function number 1, and you need to work backwards to find what the mapping is, number 2, and then given you found the mapping, you want to test out, like, if I use the kernel function, is it the same as just dotting it manually, if that makes sense. So using the kernel function to find the dot product after mapping, or actually mapping it and then find the dot product. They should be the same if the kernel function is correct. Now, the last thing I want to talk about is okay. So here's a practical example. Is it the same mapping? Root 2. Oh, it is. Yeah, this is the same mapping. Okay. So in this example here, right, there is there's no like separating. There's no separating hyperplane. But actually, if we map to R3, if we go to R3 using this nice little mapping here, there's actually a separating hyperplane. That's really nice. Hopefully you can kind of see why it's a separating hyperplane. And it just this question just wants us just to test out a few points, right? So, if you have 5, 5, what does it map to? 5, 5 might be, say, I don't know, maybe that's 5, 5, right? That could be 5, 5, I'm not sure. And we're like, okay, what does it map to? And, plug it through here, so it should be, 5 squared, 25, 5 squared, 25, and then, root 2 times 5 times 5. How'd they get to 35? Maybe they rounded it. 5 times. Got 35. That's odd. I feel like this should be 35.35. So 5, 5 using this mapping here, so 25, 25, and then square root 2 times 25. I will check this, but I think that should be 35.4. Anyways, you map it over here, and it's a bit hard for me to draw it in 3D, but it might be one of these X's. I'm just going to call it maybe this one. Maybe let's call this one, say, 25, 25, and then say 35. Oh yeah, maybe they just rounded it. That's fine. Yeah, they just rounded it to the nearest integer. Cool. Next one is they want to test the origin. Not the origin, sorry. They want to test something in the O class. So -1, -1. So maybe this one here is -1, -1, right? Let's map it across. And the thing they want to check is that it's that it's still the same class. So x is x. This one mapped over there should also be 0 or 0. And so what does map to? -1 squared, -1 squared, so 1, 1, and then root 2. Well, and it's root 2. So 1, 1, root 2. I mean, 1, 1. Let's call it this, right? And it's in the same class. Cool. Yeah. So that's all I have for today. Thank you all for your time. If you have any questions, feel free to come along to my consults and ask me questions. Thank you, everyone.